Electronic Design Automation, EDA, also known as Electronic Computer-Aided Design, ECAD, encompasses a category of software tools utilized for designing electronic systems, such as integrated circuits and printed circuit boards. These tools synergize in a design flow used by chip designers to conceive and assess entire semiconductor chips. Given the complexity of modern semiconductor chips containing billions of components, the use of EDA tools becomes paramount in their design, particularly focusing on integrated circuits, ICs, within this context. The roots of electronic design automation trace back to IBM's documentation of its 700 series computers in the 1950s, marking the inception of CAD systems. Initial CAD systems, such as IBM's Automated Logic Diagram, ALD, were crucial, running on mainframe computers and involving manual drafting of logic schematics, transcribed onto templates and punch cards for digital processing. Before EDA's advent, integrated circuits were predominantly designed manually, with some using geometric software for drafting tapes to be used in the creation of monochromatic exposure images. The process was labor-intensive and heavily dependent on manual graphic translation. Subsequent advancements in the 1970s saw the automation of circuit design, leading to the development of placement and routing tools that streamlined the design process. Key developments like Calma's Graphic Design System, GDS, and GDSII enabled engineers to digitize and edit entire chip layouts on mini computers, setting standards for modern design flows. The release of Introduction to VLSI Systems in 1980 by Carver Mead and Lynn Conway heralded a new era, facilitating the design of more intricate chips with enhanced access to design verification tools, enhancing functionality and layout precision. The evolution of EDA tools burgeoned with academic initiatives, including influential tools like the Berkeley VLSI tools Tarball and the Espresso Logic Minimizer, revolutionizing circuit complexity reduction. The formation of MOSIS, a consortium aiding student chip designers by producing real integrated circuits affordably, marked a significant milestone in EDA's trajectory. The commercialization of EDA commenced in 1981 with companies such as Daisy Systems and Mentor Graphics emerging as prominent players in the industry. The advent of hardware description languages like VHDL and Verilog further propelled EDA's growth, with dedicated trade shows and simulators making chip design more accessible. Present-day EDA workflows are highly modular, generating standardized design descriptions that interconnect seamlessly into units akin to cells. While most digital circuits follow modular design principles, analog circuits necessitate more specialized, manual design due to their unique characteristics and requirements. The continued scaling of semiconductor technology has magnified the importance of EDA tools in electronics design, catering to foundry operators, technology design service companies, and FPGA programming needs, underlining their significance in modern integrated circuit design processes. The Design Schematic Capture program is a vital component of the design flow in electronic design automation, EDA. The process involves several key steps to bring a design concept to fruition. It begins with high-level synthesis, where a high-level design description is converted into the register transfer level, RTL, to represent circuitry through interactions between registers. Subsequently, logic synthesis translates the RTL design into a netlist of logic gates. Schematic capture plays a crucial role in capturing the digital, analog, or RF-like designs, utilizing tools like Capture CIS in OrCAD by Cadence and ISIS in Proteus. Following schematic capture, the layout phase, often driven by the schematic, involves tools like layout in OrCAD by Cadence and Ares in Proteus. Electronic circuit simulation is then carried out to identify and address issues such as lithographic and fabrication defects in the design. This includes transistor simulation for accurate device-level behavior, logic simulation for digital behavior, and behavioral simulation at the architectural level. Verification processes like functional verification ensure that the design meets specifications and operates correctly. Various verification methods include RTL linting, clock domain crossing verification, formal verification, equivalence checking, and static timing analysis. Physical verification checks the physical manufacturability of the design and estimates yield. In preparation for manufacturing, tasks like mask data preparation and chip finishing are performed. Functional safety analysis assesses failure rates and diagnostic coverage for compliance with safety integrity levels. Additionally, functional safety synthesis enhances reliability by adding fault detection and tolerance mechanisms, while functional safety verification tests the design's response to inserted faults. As of June 2025, the market capitalization figures for various companies are as follows. Synopsys at $75.4 billion, Cadence Design Systems at $81.1 billion, Ansys at $29.4 billion, Altium at 9.01 billion Australian dollars, Siemens at 170.7 billion euros, and Zuken at 112.9 billion yen. It is important to note that Synopsys had announced plans to acquire Ansys in 2024, with the deal expected to close in the first half of 2025. Moving back to December 2011, some defunct market capitalization figures were reported. Mentor Graphics at $2.33 billion, Magma Design Automation at $507 million, and Springsoft at N6.44 billion. Siemens later acquired Mentor Graphics in 2017 and renamed it Siemens EDA in 2021, while Synopsys acquired Magma in February 2012 and Springsoft in August 2012. The landscape of EDA companies often involves acquisitions of smaller firms possessing compatible technologies. Many industry leaders are the result of mergers of such smaller entities, with tools being designed as complementary components for larger software suites in the realm of digital circuitry. Presently, there is a shift towards placing entire electronic systems on a single chip, prompting the integration of analog design and mixed systems into new tools. Machine learning techniques have become prevalent in integrated circuit design processes, enhancing efficiency and outcomes across stages like high-level synthesis and sign-off. EDA vendors have incorporated optimization engines utilizing similar machine learning principles into their tool chains to further streamline operations. The open-source EDA ecosystem has seen significant growth, with initiatives such as the Open Road project, launched as part of DARPA's IDEA program, introducing an RTL to GDS flow capable of completing designs without human intervention. Conferences like ORConf and the annual FOSSI Foundation Roadmap sessions now feature dedicated tracks to showcase advancements in open-source EDA technologies. In the realm of electronic design, wire routing, also known as routing, plays a crucial role in the creation of printed circuit boards, PCBs, and integrated circuits, ICs. It follows the initial placement stage where the position of each active component is determined on the board. Routing involves adding necessary wires to connect these components correctly while adhering to all design guidelines for the IC. Autorouters utilize different algorithms such as maze routing, Lie routing, Hadlock routing, and more, each offering distinct features and capabilities. Routing algorithms typically involve global routing to outline a general path for each net, followed by detailed routing where nets are routed individually, and any conflicts are addressed iteratively until all connections are successfully established or a termination criterion is met. Routing strategies may include assigning wiring layers for different directional wiring to manage power supply and crosstalk effectively, with each approach bringing its own set of advantages and drawbacks. The development of EDA software is closely tied to the evolution of technology nodes. Semiconductor foundries encode their specific properties, such as transistor models and design rules, within proprietary file formats used by EDA vendors. These files collectively form the Process Design Kit, PDK, usually a collaboration between the foundry and an EDA vendor. PDKs are typically tailored for compatibility with a specific EDA package and are treated as confidential information, often safeguarded by non-disclosure agreements, NDAs. The delivery of PDKs to designers might involve encryption or partial information disclosure. Various software applications for electrical simulation, covering analog, mixed signal, and electromagnetic fields, offer different features and support levels, such as schematic design, simulation capabilities, and PCB editing. Some notable platforms include Advanced Design System by Keysight EE-SOF EDA, Circuit Logics by Logic Design, LT-SPICE by Analog Devices, and MicroCap. While the latter two are free proprietary tools based on SPICE technology, MicroCap transitioned to freeware in July 2019 after Spectrum Software, its parent company, closed, whereas LT-SPICE has long been freely available. Altium Designer, previously known as Protel and developed by Altium for Windows, had its latest release on October 10, 2024. The platform supports schematic design, simulation, and PCB editing. It offers a user-friendly interface, available in multiple languages, and allows imports from software like CAD, Allegro, and Eagle, while supporting exports to formats such as Gerber, DXF, and PDF. Additionally, Altium Designer provides scripting support for languages like Delphi, JS, and VB. Zuken's CAD Star, Board Designer, and Vizsla software, designed for Windows, was updated to version 22.0 on August 31, 2022. The platform excels in features like schematic and PCB editing, along with signal integrity and power integrity analysis. Supporting imports from PADS, OrCAD, and Protel, it also enables exports to formats like Gerber, Exelon, and PDF, while providing COM and macro scripting capabilities. Circuit Maker, a product of Altium for Windows, released version 2 in July 2021. This software focuses on ease of use and functionality, offering schematic design and PCB editing tools, although simulation features were removed in the last update. Circuit Maker allows imports from various sources like Gerber and DXF and supports exports to formats such as Gerber and PDF. Wine compatibility is available for this platform. CR5000 by Zuken, a POSIX-compatible software, was updated to version 13 on May 17, 2011. This platform supports schematic design, simulation, and signal and power integrity analysis, catering to both English and Japanese-speaking users. With import capabilities from formats like EDIF and DXF and exporting options to PDF, Gerber, and Exelon, among others, CR5000 also provides scripting support for additional functionalities. Zuken's CR8000 software for Windows, Unix, and Linux was last updated on June 30, 2020 to version 2020. This platform offers advanced functionalities for schematic design, simulation, and signal and power integrity analysis in multiple languages, including English and Japanese. Supporting imports from various formats like EDIF and DXF, CR8000 allows exports to formats such as PDF, Gerber, and ODB++, with additional features like request-based exporting to other formats. DesignSpark PCB, developed by RS Components for Windows, was updated to version 9.0.3 on July 8, 2020. With a focus on user-friendly PCB editing and spicing features, the software supports imports from Eagle, DXF, and EDIF, while offering exports to formats like Gerber and Exelon. This platform provides a seamless experience for English-speaking users and supports a wide range of design functionalities. The development of open-source EDA software bundles is progressing quickly, with the DARPA and Google's OpenRoad project playing a significant role. The OpenRoad project offers a comprehensive set of tools that range from high-level synthesis to layout generation. This flow incorporates YOSYS for logic synthesis, OpenLane for physical synthesis, and is specifically tailored for the SkyWater 130nm PDK. Currently, this flow is utilized for submitting designs for free fabrication at Google. High-level synthesis software, which is vital for designing both ASICs and FPGAs, facilitates editing and verifying code in popular hardware description languages such as VHDL or Verilog. Some tools provide a higher level of abstraction, enabling synthesis from languages like Chisel or Spinal HDL, thereby allowing formal verification of HDL code. Notable software like GHDL serves as a VHDL analyzer, compiler, and simulator, while Icarus Verilog and Verilator offer solutions for Verilog processing, with Verilator recognized for its exceptional speed compared to commercial simulation tools. Various developers have contributed to the landscape of electrical engineering software, offering programs like Altium Designer, ANSYS Electronics, and KiCad for diverse design needs. Additionally, free software options are available for IC physical synthesis and layout, with tools like Electric and Magic catering to VLSI layout design requirements. Furthermore, the realm of schematic editing and analog mixed signal simulation is supported by software such as NuCap, InkSpice, and QUCS, each offering unique features for circuit simulation. For PCB design, a range of software like FreePCB, Fritzing, Gutta, KiCad, and PCB R&D provide solutions for various design aspects, from layout creation to auto-routing capabilities, catering to the needs of hardware engineers in electronic circuit and PCB design.